Hi, this video is using the Biot-Savart Law to calculate the magnetic field near a long wire carrying current. So the Biot-Savart Law tells us that if we look at some element of current carrying wire following some path ds, the magnetic field at some point away from that element of wire is going to equal the permeability of free space mu naught divided by 4 pi times the current times the cross product of my path element ds with the direction of the radial distance from that element of current to where I'm looking for my magnetic field, r hat, divided by that radial distance r squared. So if I have some segment of wire, the easiest way to describe what's happening is to say that the wire lies along the x-axis, and where I'm looking for my magnetic field is the origin of that totally arbitrary x-axis. And I'm going to be some distance a away from the wire at my origin, x equals 0. Now, there are a number of ways I could try and describe my radius. I could look at my y-coordinate, I could look at that distance a, and the size of my radial path would be equal to my x-coordinate squared plus that distance a squared, added together and take the square root. That works. The cross product and the integral that come with it get really messy needlessly. I could also express it using an angle. And the angle that I'm going to choose is the angle from this distance a to my radius. So the distance that I have, if I know my distance a, well, I have a 90-degree triangle. So this is adjacent to my angle, r is my hypotenuse, so the size of r is just going to be my distance a divided by the cosine of theta. That really is going to bail me out with trying to figure out my radial location, r hat. Now, trying to express it in terms of coordinates x and a, and then dividing by the magnitude to normalize it to make it a unit vector, that's a mess. But since we're using this angle, my x component would be technically minus the sine theta in I hat, because as I've laid things out, well, doesn't matter, negative, positive, going in each way. When we take the cross product, that I component's gone. And in the y component, this is adjacent, so it would have the cosine of theta in the y direction. Well, my path element ds is just going to be a change along my x-axis in the x direction. So when I take the cross product of those, as I said, the I term, it's gone. We don't care about it anymore because I cross I is 0. I cross j gives me the k hat direction. So that means that my cross product is going to be my path element dx times the cosine of theta in the k direction. K direction is positive coming out of the board. Well, if I use the right-hand rule for current, if my thumb is the direction of the current, my fingers would form the magnetic field, so my fingers should be coming out of the board. That direction checks out. Now, we either need to get rid of theta or get rid of x. And we already said we're using theta to get rid of x, so let's get rid of dx. So to do that, I need a way of essentially substituting out that dx. So my location x here is adjacent my angle theta. So I have my side A, I have my side x, the tangent of my angle theta is just x over a. So x would be equal to my distance a times the tangent of theta. And for my substitution, dx d theta is equal to a over cosine squared theta. Well, dx then would have to be a d theta divided by the cosine squared of theta, times the cosine of theta in the k hat direction means I can cancel one of my cosines. So in terms of angle, my cross product is going to be my distance a times the integral element d theta divided by the cosine of theta in the positive k direction. And 1 over r squared is just going to be 1 over this, which is cosine over a. So I have the cosine of theta over a squared. So if I plug those pieces into the Biot-Savart law, well, a d theta over cosine theta times cosine squared theta over a squared, I cancel a cosine, I cancel an a, so that means that my integrand that I have to process, dB, is going to be mu naught times my current divided by 4 pi a, the distance away from the wire, times the cosine of theta d theta in the k hat direction, which isn't a bad integral to process at all. So if I just want to take a look at the size of that integral, since like I said, the direction is just coming out of the board, well, the integral of cosine is sine. So for a fixed segment of wire where we could determine the starting angle and ending angle, the magnetic field would be mu naught times the current divided by 4 pi, the distance from our wire to where we're looking, times the sine of our final angle minus the sine of our initial angle. But what we're most interested in is looking at the problem of a wire that's practically infinite. Well, if we think about limits, as I let x go to positive infinity, that angle is going to keep getting closer and closer and closer to 90 degrees from the vertical. So the sine of plus 90 degrees would give me 1. As I let x go to negative infinity for my angle theta 1, I keep getting closer and closer and closer to an angle of negative 90 degrees, which the sine of negative 90 degrees is negative 1, and 1 minus negative 1 gives me 2. So for an infinitely long wire, I get a magnetic field that would be equal to mu naught times my current divided by 2 pi and my distance away from that infinitely long wire. Thanks for watching.